Let me introduce our third speaker for this afternoon session, Antonio Ocello. He is a postdoc researcher at Ecole Polytechnique. His research interests lie in generative models, sampling, and these machine learning problems. So in this talk, he'll be speaking about analysis of noise schedules in score-based generative modeling algorithms.
So I think I will not needing the microphone because like I gotta put it, my citizenships help me like being loud, so I think it's gonna be fine over that point of view. So thanks and thankful to the organizer. I'm really happy to be in London. Like I've been during the first week during the mini lecture, and I'm very glad to present like the last a paper that I did in collaboration with colleagues in my previous university at Sorbonne University. So what we want to deal with is how to optimally trade like noise scheduling. And for those of you who are like in the first week, it is like a little problem that originates in when you're looking at these class of models, and it relies on optimizing the kind of architecture that you are exploiting. So let's like dive in. Even though there are slides of introduction, even though after like all the talks I've had today, there will be of no need. So what are generative modeling? Like everybody knows, we have the sampling, we have data that we want to that we have collected, okay, and we want to generate new instances like from this data. So we try to build a bridge with an easy to sample distribution. And from that, to try to find a link from going to easy to sample to this new data. So, like again, this has been introduced plenty of times. You have like some kind of images, which are the example that everybody wants to look at, that everybody is looking at this moment. Even though right now it's more a video, but like let people give images about kittens, and you want to generate new kittens. And so you try to do, there is like a forward phase like where you destroy the information that you have, and a backward phase, we can try to reconstruct the information that you have. And so the thing is that we want to do, we want to do this thing optimally, and we want to like optimize the kind of resources that we have. Okay, so the computational power that we have. And so the forward process, as we have described today, like it's generally described as Norton-Uhlenbeck type process, okay, and this is the easiest way to destroy the data, where this type, and it's the easiest one because you know everything about it. You know, like you can sample exactly, like there is like this equation that is valid just in law, like have like an explicit you have a closed form of where like the what is the law of xt at each time, and you know what is the stationary distribution. And if you consider like a specific time interval, you can use like as we have been presented today, but you can use like this time reversal formula, and if you try to approximate the things that you're missing, you can give a way to construct new samples from the data that you have at the beginning. The problem is that like the intensity that what's going on is that you try to add more and more intensity, and on a theoretical point of view, if you know this, you can give new samples, okay. But like when you go into the pipeline, it's very hard to tune all the different parameters, because at the end of the day, what you want to construct is like an algorithm, and you want to there's a lot of parameters that need to be tuned, and like maybe we're gonna be focused today on just one parameter that and we try to tune it like optimally, or try like give some like perspective or attempt to how to tune it optimally. So the thing is that like little is known theoretical about what is the best practice to tune this parameter, okay? And like and there are like a lot of there are some empirical results that show that actually like tuning, so the discretization of the backward SDE that you're looking at really do matter, and really has an impact on what are the quality of the data and how you're really using the computational power, okay? And so, and this is this paper by China in 2023, the one that like gave the what is now known as the cosine schedule. Okay, so this is like what this which is represented in the paper like as this God-given schedule that tells you like how to optimize the power of your computer to really catch the difficulty of this task. Because as you can see, as we said, we have seen before, like in the Ocello process, like you have like you forget about the initial condition in exponentially fast. So since you're more interested in sampling what happens at x0, you want to go slowly to really capture what's going on at initial position. And like when you are close to the Gaussian distribution, you stop caring about what are the properties of your score, and want to capture that in a mathematical form, which and two things. Possibly like give a theoretical validation of this cosine schedule, if possible. And second of all, like give like an optimization algorithm that would be a help practitioners to really capture how to go through the flow of distortion and Kullback. Okay, so the theoretical point of view that we're gonna use is very easy, especially to this kind of public. And we just gonna consider like a time change, okay, that depends on a parameter beta, that is how fast we go through the trajectories of our Kullback, okay. So if we have, this is still an Kullback, but is a time inhomogeneous Kullback. And then the kind of discretization that we're looking at is gonna be like uniformity. And so we're gonna capture with this parameter beta, with this function beta, how we go through the flow, with which intensity we go through the flow of our SD. So this is gonna be the time change, like the time reversal, and we need to take into account what are different errors that we're looking at, and piling that up, maybe trying to find like a proxy for what is the actual error what is the bound on the distance between our samples, the data distribution that we want to recover, and what the algorithm gives us, okay, and want to be as close as possible as we can in different kind of divergence, let's put it this way, or so convergence result can be classified, let's put it this way, into two macro groups. A huge macro group that like really interests like what happens when looking at KL divergence, and like other results that are like a subclass of this KL divergence class, where like look at total variation or other divergence that can be linked to the KL divergence, okay? And this is what we're gonna do is gonna be mostly like focused on what people at Ecole Polytechnique did, like last lecture and put on archive last September, the paper we were talking about before, the one by Giovanni Conforti, Andrew Mus, and Marta Gentiloni Silveri, which we talk about like really gives. I think this is the state of the art about with minimal assumption on the data, what is the convergence bound that you can look at. And then there is like another class of paper that like try to look at what happens in Wasserstein distance, and not but directly in Wasserstein distance without going through the KL divergence. Because like if you have a bounded support on your on the data distribution that you want to look at, you can bound the Wasserstein one distance of what you're looking at with some with the KL, and so you still go back to the first class of models that the class of paper that you want to look at. Okay, and I'm trying to convince you that like there is an interest in looking at this class of models, to look at convergence bound for this kind of results for these purposes, without looking at what happens in KL divergence. So as I said, there is no problem. The problem here is that there is no explicit error that depends on the noise scheduling, on the parameter beta, on the way we go through the flow that we are considering. And so now we're gonna consider like with the time change that we have considered before, we can rewrite like the two. So we said that when we look at the Ocello gives a sort of interpolation between two distributions. What happens at time 0 and what happens at times infinity. So these two cofactors are going to be where, like, if you were to use like the classical Ocello process, like without the time change, it would just be exponential minus t, and on the other side, square root of 1 minus exponential minus 2t. And so these are just cofactors and tell you how much you are like destroying, like which intensity you are destroying the data at the beginning, and which intensity you're pushing your data toward a Gaussian distribution. So looking at that, like what happens that here when we look at what happens at time capital T, now we have the first error, type of error. Okay, like if you pay attention in the talk about Yakim, you would see that like there were three types of errors, okay? And like this is the first one. This is the mixing time error. So whenever you go at time t and you want to go back, you don't actually use what happens at time t, but you switch what happens at time t with the stationary distribution, which is a Gaussian. Okay, so this is the first type of error that we're making. So the second type of error that we're making is that like actually like everything depends, like the backward LD that we're looking at depend on the score function. And as we said, as we have been considering, like we approximate the score function with explicit neural network. A lot of tricks. I don't want to go into any details, but basically what happens is that here we have like the second type of error. We try to we start from the stationary distribution, and then to go back, we approximate the score function with some architecture. And third of all, like the second type of error that we're making is that, like as we have considered, as it's been said in the talk, in the question part on Yakim's talk, like the thing is, the way we go back in time is not linear. It doesn't have a linear structure in the SZ. So what the problem is that we cannot simulate exactly what's going on, and so that's why we need to use we need to discretize the interval 0t and use for example Euler's T non-exponential integrator scheme that exponential integrator would just take into account the fact that you have a linear part times a non-linear part. So, but basically think about Euler's T. And so the thing is that here we have like the third type of error, and of course, like since this is the kind of approximation that you're making in the convergence bound, we want to retrieve the three type of errors, and actually what we're interested in now is like show what is the dependence with respect to B. So if you think, so once we are into this setting, we can retrieve, like we can reinterpret what Giovanni, Marta, and Alan did in their paper, and give like a convergence bound with respect to that directly gives you like the dependence with respect to the parameter beta. And this is actually a quite nice optimization problem in the sense that if, for example, like you consider this kind of parametric, these parametric functions, okay? You put all the beta to stop at to arrive at the same point, capital T, okay? But doesn't mean it means that actually, like you go, yeah, you arrive to the same point. You arrive to the same point, capital T. While doing this, what happens here is that like you sort of kill the term because all the things will have like the same final point. So the third term will be destroyed somehow. And now what happens is that like you have like some kind of dependence of beta that just depends on the integral from 0 to t. And now we have two terms. Okay, they are opposing one another. There are the coercive. There are that give to your optimization problem a coercivity structure. Okay, so it means that like whenever the area under the curve like explodes, these terms explode, and whenever it vanishes, this counterbalance the other problem. So you just have like you know that like looking at this optimization problem, you expect that you have a minimal solution. It's kind of the best way to exploit the power the power of your computer, and you try to understand what's going on. The trick here is that doing things can be like quite challenging in the sense that like this term, so the way you're gonna having errors on the way you learn, like the score depends on the discretization that you're looking at. So it's quite more complicated that could be thought at the first glance. Okay, so we try to do some numerical analysis, like I don't know if I should put like really toy model in the sense that we consider just like a Gaussian distribution and try to understand what happens in Gaussian distribution, especially because in Gaussian distribution we can have like a full understanding on all the quantities and looking at the optimization problem. And so the thing is that we try to see if on this parametric class of beta, we try to understand what is the best one, and also we want to understand if the kind of signal that we are retrieving, like the bound that we are considering here, is a bound that is tight with respect to what we're considering here. If this is the case, we could just say that okay, we just optimize the bound, find what is the best beta, and and propose this beta to a practitioner that wants to exploit the best that he can, like it's called the computer power. Just one reminder, like if you were at the last, I guess, lecture, yes.
On the slide that you had opened before, how do you are you estimating the epsilon thing, like the score approximation error?
Yeah, we try to estimate everything. Like we try to estimate everything. Yes.
And I agree.
What?
Are you really doing it for a specific model where you estimate it, or is there a theoretical way to estimate how it changes from time step to time step?
We gave like a really naive like Monte Carlo estimation for this quantity.
Yeah.
And yes, this is what we have done.
Yeah, thank you.
Yes.
Sorry, this is a very naive question, but for a Gaussian, if you know the initial condition, the measure, the score there will be just the like you have an explicit formulae for that.
Yes. But the thing is that we want to make errors. We need to understand like we want to make errors for two things, because if this error would be zero, like you could optimally solve your beta, but this is not what happens in real life. So that's why you want to make some errors, and you want to see how this error like propagate, like how this error impacts the choice of beta. So that's why, like, even though this function is linear, you could do everything like perfectly, but if you know that the sample that you're looking at is Gaussian, you will never think about doing generative models, to be honest. So this is a really like a simplified setting where to do a proof of concept. See, yeah. So I was saying that like the way again, if you were at the last lecture of the Valentine gave on the first week of this program, you see that like he was saying that he was showing that actually what actually matters is not very like is not the how beta what is the function of beta, but actually how fast you are destroying your how fast you are destroying your signal. And he was giving like two major examples. There is the linear scheduling that takes you from 1 to 0 like linearly, but like with respect to m, and inversely like for sigma. And what is and gives like the cosine schedule. The cosine schedule will be like with respect to m, so it will like sine and cosines with respect to this kind of things. So we don't match exactly like the linear and cosine, but we are close, sort of close to what has been proposed. And so the thing is, like looking at this naive example, we can see that that the bound sort of like mimic what happens with respect to like the Ecole divergence between like the initial and the final and the sample distribution. And but in very different example, and we can see that there are different things that we can analyze even on this simplified setting. So this is a tropic Gaussian. Everybody has the same. Everybody has the same. Everybody has the same variance. But whenever we change the structure of the variance, we could see that the match is still fine, but is not as perfect as we want, as we would love to be. And this would give us like insight on maybe that give like noising everything, all the coordinates in the same way for the same direction would not be the best thing to do. Maybe we should do some adaptive kind of noising. So having beta that not only depends on time, but also depends on the direction that we're looking at. But this. So these are the results for the numerical experience, but now I just want you to focus on like this bound, and like if everybody who's like experienced more than I do in like how to do estimation and how to do estimation would tell us that there is a huge problem in this bound. The problem in this bound is that like to compute it, we need quantities that actually are very, very difficult to compute. So if you have like just samples and you want to give to estimate what is the Ecole divergence between like two quantities, like it's very hard to compute that. And so that there's no naive estimator, and the naive estimator that have been proposed relies on k-nearest neighbors that do not perform well when like dimension increase. Even dimension 50 is very expensive. So that's why we try to like consider like what happens in Wasserstein bound and in Wasserstein distance, and like looking at Wasserstein distance, like we are considering like again a simplified setting. So we just consider like where P0 is C star of concave. Okay, so a very simplified setting. And still in this simplified setting, we can see that the bound that has been proposed in the literature is still not quite tight, and we're going to see it in the numerical scheme. But again, what happens is that we have three sources of errors, okay, and we try to combine the three sources of errors with respect to what is beta that we are giving, and with the beta we're giving, we try to optimize. And so again, now here, like the quantities can be estimated in a more accurate way. So that's why we try. That's why for my point of view, like going and understanding what happens in the Wasserstein distance with quantities that actually depend on the Wasserstein distance is it can be interesting. And so, like looking at the simulations, we could see that the bounds actually you still sort of mimic what's going on. So you got like the minimum in the same place. More or less, but the match is less striking. So the second thing that we need to look at is we need to like push the understanding of what happens in the Wasserstein distance with respect to these models, and give convergence bound on Wasserstein distance. And then we try to prove to give to understand what's going on when for more different example that are beyond like the Gaussian distribution, and we see some sort of match, even though like the bound we can see it oscillates quite a bit. So then we propose like a naive scheme to understand how to tune the beta, but I think there are plenty of things that can be done into this kind of direction, and especially the problem into giving optimizations with respect to beta is like what we have considered before, in the fact that you start your training, but then the kind of scores, the estimation that you have given, like depends on the beta that you have chosen. So you have like something that needs to be sorted, and so plenty of room to improve. And on that, there are some references, and I thank you for your attention.
Any questions?
Can you maybe remind us of how is the L defined on the last slide in the algorithm where you say argmin of MEFKL in line 6? So is this an empirical? Sorry, I think I missed this. Is this empirical thing or is this from the slide before?
No. This is the empirical estimation of your scheduling that with respect to like the parameter theta. And I'm putting a lot of things under the rug. And also the thing is that like you take, so the way the algorithm works, like you take some batches, and after the batches you try to see like how to change the beta, okay? And what happens is that like what happens is that so after I think it was 50, you were changing what's going on with beta to update the value of A in the end, and trying to get if like was very striking like to optimize on beta. But I don't think that this on this example was very effective. I think we should have pushed into more complicated example.
And how did the final beta look for this example then?
Very closer to the cosine schedule.
Okay. Yeah, well, that's nice, right? I mean,
yeah, it's a proof of concept. Let's put it this way.
Questions? That we state this, you have the condition of it, and you have the integral of the beta is infinite. Is it a technical one or it has some practical?
No, not really. In the sense that like what you want to do is that you want to really follow. You really want to follow like the trajectory that you're looking at. So basically, if this integral is finite, it means that like you don't go up to the Gaussian, but you stop before. That's the thing. Like you have like if it is finite, it means that you're going too slowly to actually reach the Gaussian. And this is like the technical thing that tells you like is the technical assumption that it tells you like okay, you're converging like in theory like to the Gaussian at the end, even though like you do things from 0 to capital T. So just for it to be like a real time change, it needs it to be to explode that. Thanks.
If we have further questions, we can discuss during the coffee break. And we have one last talk at 4 o'clock. Please continue.